Thanks, Jeff, for the introduction. So, hi and welcome to this Vitis webinar. We will focus on the creation and optimization of C++ kernels in the context of the Vitis flow. C++ kernels are the most natural way to implement an algorithm for Vitis, and it does not require the knowledge of a hardware description language such as VHDL or Verilog. I will present the flow and illustrate the optimization concepts with a demo design based on the Traveler Salesman Problem algorithm. And I will show you how this algorithm runs orders of magnitude faster on an FPGA compared to a CPU, and also faster than the GPUs, while requiring a very little amount of resources on the FPGA. But before jumping into an example, I will briefly discuss Vitis and how it helps implement an accelerated algorithm to target a Xilinx platform for heterogeneous compute, cloud-to-edge deployment, including AI enablement. Vitis isn't just one tool, but an ensemble of compilers and libraries to compose and assemble your application and all its processing blocks onto one predefined platform. So think of Vitis as a unified software platform. It also enables the development of embedded software and accelerated applications on heterogeneous Xilinx platforms, including FPGAs, SoC, and Versal adaptive SoCs. It's a programming model for accelerating edge, cloud, and hybrid computing applications. You can leverage integration with high-level frameworks developed in C, C++, or Python using accelerated libraries, or use RTL-based accelerators and low-level runtime APIs for more fine-grained control over the implementation. Basically, you can choose the level of abstraction you need. Drivers are also provided alongside runtime APIs, and as a developer, you target a pre-customized platform that comes with predefined hardware ready to communicate with the runtime drivers, as well as customized lower IPs to connect to the platform. Xilinx refers to kernels for any accelerators implemented onto the FPGA. In the context of this webinar, we'll focus on the C++ kernels. But besides C++, note that it's also possible to use accelerators written in RTL or designed with Model Composer. Vitis then gives you all the tools to compile, emulate, link, program these accelerators onto a predefined platform. One of the advantages of designing with C++ kernel is that the full application can be C-based. The C++ kernels are going to fill the hole in the donut, meaning that it will use the available free space on the platform. The platform becomes the receptacle for the kernels, and Vitis attaches them to the platform during the compilation. Incorporating a C++ kernel into a platform is done via the Vitis V++ compiler, which first leverages the Vitis high-level synthesis tool, known by its acronym HLS, to parse and synthesize the kernels into an archive file with an extension .xo. Secondly, V++ links this kernel and any other kernels associated with your application to the platform to create an executable XCL bin. Let's now move to a section that discusses the optimizations of the C++ kernels. In essence, optimizing C code, which is inherently sequential and untimed, consists in applying three fundamental optimizations: pipeline, SIMD, and DATAFLOW. The three can be applied with directives inserted in the code to allow the HLS compiler to create a well-balanced hardware that uses the right amount of parallelism to accelerate your algorithm. Let's now briefly discuss the three fundamental optimizations, starting with pipeline. The pipeline optimization instructs the tool to process the inputs in scope at each clock cycle. If we take the example of a loop that's not pipeline optimized, then one loop iteration must complete in the generated hardware before the next inputs are read for a second iteration. But when pipeline is applied, new inputs are continuously read while the body of the loop processes previous inputs. This guarantees the processing hardware keeps busy and continues churning on data continuously. This ensures the processing pipeline is filled. If your algorithm relies on nested loop, you might choose to pipeline the inner loop or the outer loop. Pipelining an outer loop forces the inner loop to be unrolled, since you're asking it to process at each clock cycle. It's obviously better for performance, but it will require more resources. Pipeline can also be applied to functions, but depending on the complexity of these functions, it might then force too many subfunctions or loops to be unrolled and create impractical hardware. In the example we'll use later in this session, you will see that we chose to pipeline a loop, which is what developers most commonly do. Here's a code example with a pipeline loop. It reads an array called A and visits it based on the index called X. The pipeline directive requests that this loop reads one element of the array at each clock cycle. Pipeline can implicitly create parallel hardware, for example in the case of nested loops, but parallelizing hardware can be done by looping through instantiations of a subfunction or using the unroll directive. Another technique at your disposal is the vector data type introduced in Vitis HLS. It makes it convenient to model SIMD type operations. SIMD vector types are characterized by two parameters. First, the type of element that the vector holds, and second, the number of elements in that vector. Vitis HLS provides a templated class, HLS : vector, to describe predefined SIMD variables. All the operations performed using this type are mapped to hardware during synthesis that will schedule these operations in parallel. The following example shows a 16-element vector of integers. The third optimization I wanted to discuss is DATAFLOW, often referred to as the task parallelism optimization in HLS. The DATAFLOW optimization is useful on a set of subfunctions and loops as shown in this code snippet. Using this series of sequential tasks, DATAFLOW optimization creates an architecture of concurrent processes, as shown below. DATAFLOW optimization is a powerful method for improving design throughput and latency. Note that DATAFLOW optimization potentially improves performance over a statically pipelined solution. It replaces the strict, centrally controlled pipeline stall approach with a more flexible and distributed and shaking architecture, using FIFOs or ping-pong buffers to connect between the tasks. The replacement of the centralized control structure with a distributed one also benefits the fan-out of control signals, for example register enable, which are distributed among the control structures of individual processes. If you look at the code example on the slide, you see that there are three subfunctions which happen to follow a very important guideline for HLS, which is that the code should as much as possible flow with a load, compute, and store, in which the load gathers the data and stores it with on-chip memory. Then the compute will use that data, and finally the store will write it back on the global memory. Several other directives are also available in Vitis high-level synthesis. They do help support the three major optimizations we just discussed. For example, you can partition and reshape memories to help access more memory ports in parallel when needed, to in turn improve the initiation interval. You may also tune the results by choosing a particular form of operators or memories using the bind up and bind storage directives. Another fundamental aspect of designing with C++ kernels and optimizing performance is understanding how the code connects to the hardware available on the platform, because here also there is some flexibility, as we'll see. When designing the kernel and coding, you will use arrays, scalars, and perhaps streams for the top function arguments. Streams are both a natural and efficient way to move data without the need for storage, and could be used for kernel-to-kernel connections. Streams in Vitis high-level synthesis are modeled through a C++ class to represent the concept of FIFOs. So overall, once V++ compiles our C code, it looks at the ports of the function to accelerate, and in conjunction with the interface directive, it connects the post-C synthesis synthesized RTL from the kernel to Axie4 connectivity blocks that are automatically added by the tool and that you may configure through the interface directive. The one level of detail down that I want to show you on this slide is that actual adapters are inserted to embody this connectivity at a low level. These adapters are pre-made blocks of RTL with control logic and local storage. The M_Axie adapter is a block that high-level synthesis inserts to map arrays and pointers, and the AXI-Lite adapter stores scalars as well as internal control registers necessary for the platform to set up, start, and stop the kernel. Here is a basic example with 3 pointers and a scalar. It performs an addition on a series of integers and does so for a number of elements determined by the value of the input scalar size. It looks straightforward, and the Vitis tool chain assigns all these 3 pointers to the same adapter, since they are all referred to the same adapter with the interface directive, as per the bundle keyword. And as a result, in1, into, and out are connected to a single adapter named gmem. After C synthesis, you will realize that the throughput isn't maximum. The initiation interval is 2 when we were expecting an II of 1 for maximum throughput. If you remember what we discussed about initiation interval, it means that it can only process inputs, outputs every 2 clock cycles. The reason for this limitation is that the m_axc adapter, although being full duplex, can only process either 1 input or 1 output at a time. And here we have 2 simultaneous inputs, in1 and in2. We can also confirm the bottleneck in the schedule viewer of the Vitis HLS tool. It's another tool to help understand how the operations will be sequenced in hardware. The solution to this performance bottleneck is to assign separate adapters to both input in1 and in2. In the new code shown on the slide, in1 has now its own adapter, and the C++ kernel can now function at a full throughput with an II of 1. But there is still something to improve. The physical interface is 32-bit, which is only natural since we are using integers, but suboptimal when you consider that the hardware platform might use much larger buses. For example, in the case of Alveo, these buses can be as wide as 512 bits. So why couldn't the platform enlarge to 512 by itself? The problem is that in the original code, there are no indication for the compiler that the data could be aligned to 512 bits. So we'll use a coding trick to make it unequivocal that our data can be aligned on chunks of 16 integers, which represent the 512 bits the compiler wants to see. Note that if we had been using arrays of constant sizes, we wouldn't have to use that coding trick as long as the data could be aligned to 512 bits. But we are not quite done yet. Now our interface is wider, but the body of our loop in the kernel is not taking advantage of this larger width, as there is only one pipeline loop processing one element at a time. So what we need is to pipeline with a factor keyword modifier to implement the parallel execution of this loop on different data elements. The factor we'll choose here is of course 16, so that it matches exactly the number of data points that we have access to in parallel. We can now then process the whole interface width continuously at each clock cycle. And we can verify the parallelism in different ways. One is to look into the schedule viewer, and another confirmation can be checked in the bind report, which would list all the hardware adders implemented in the design, and we can see that there are 16 of them as expected. So to recap, we saw that different C types for the top function argument are usually mapped onto AXI4 connectivity, and that the low-level adapters can be controlled and optimized to help the compiler implement a wide interface. To verify with a great deal of precision the implementation, we can review the waveform generated by the high-level synthesis tool and see exactly at the clock cycle granularity what's happening in the design. Here I'm running a co-simulation with 1024 integers, and I can see that I get 64 clock cycles carrying the whole dataset through the kernel. I'd like to tie back this specific optimization to the use of vector types, since the developer could create types that would use the full width that the platform offers. So here, if the width we are trying to match is 512 bit and we are using integers, we can create a vector of 16 integers. Then the alignment is implicit, and the only optimization to perform is to duplicate the adapter. Compare this to what we just discussed, and you might agree that the vector type coding style is a little bit easier, as it does not require the coding trick on the loop index and no directive is required. I would now like to show how a C++ kernel can implement the traverse salesman problem algorithm very effectively with high-level synthesis as part of the Vitis flow. The traverse salesman problem is about finding the shortest route, connecting different points, and these points could be, for example, cities. This problem is solvable by making many trials, but this number of trials grows significantly as the number of points to connect gets larger. Here we're searching for an exact solution and all the possible routes are tried, one after another. To get started, we need the distances between all these points, which amounts to the square of the number of points, but this isn't a whole lot of data since we only have a few cities. Still, it's quickly an enormous amount of calculation since the number of permutations goes by the factorial of the number of points to consider. The answer for the shortest route is simply a scalar that's stored in the axi-light interface. As a reference to our discussion about the TSP algorithm, I'm using a presentation from a 2019 C++ conference titled Faster Code Through Parallelism on CPUs and GPUs. I like the presentation as it gives a good amount of information about the coding styles and performance level that can be expected on CPUs and GPUs using different coding styles and C++ compilers. I wrote down the link on the slide. The talk is available on youtube.com. During that conference session, several benchmark numbers are discussed for the different tools. There is a mix of modern C++ languages with some libraries and Pragma-based tool as well with OpenNP and OpenACC. In essence, these language extensions can accelerate performance a great deal for the CPU, but the GPU provides yet another level of acceleration altogether, and that's orders of magnitude faster than the original code. And of course, we wanted to compare to FPGA, which is what we'll do in the next few slides. But what's the approach for FPGAs? The initial distances are sent by the host, and once they get loaded onto the FPGA, there are a few critical pieces for the compute. Storing these distances onto on-chip RAM and even making copies of this RAM right when we load the data is critical. Then we need to come up with a very efficient mechanism to generate the permutation to cycle through them as quickly as possible. We choose an alternate method compared to the C++ built-in next permutation function with a method based on the factorial number system and the lemma codes. The code describes quite a few operations, but notice that the data types are limited to integers and char for the loop index. These are very efficient data types for an FPGA, more so than manipulating floating point numbers, and for this section of the code, there is no need for floating points anyways. Now for the lookup. It's the second most important aspect of the design, and these distance data points need to be implemented with on-chip memories with parallel accesses. How do we know it's on-chip memory? Simply because it's a C array declared with the C++ kernel and not present in a top port list of the kernel. Then how do we know the accesses are parallel? Simply because we are using a RAM configuration that allows one port for writing when the distances are read from the global memory, and multiple read port, since we are going to need to read multiple distances at once to calculate one route. This RAM configuration can be explicitly called for using the bind storage directive and setting its value to RAM_1WNR for one write and n reads, but the compiler should otherwise be able to apply this configuration automatically. Finally, the 32-bit integer ret holds the root value and performs a summation of all the necessary distances looked up by the permutation array we just discussed in a previous slide at once, and sustain the calculations at every clock cycle. Let's now look at the code and the tools in more details. In this demo section, we take a deeper look into the code and the tools. Here is a makefile to run Vitis. There are many examples of those on the Xilinx GitHub repositories. You can see here that I am targeting an Alveo U50 acceleration card through the platform variable. The file specifies all the settings and flags for the V++ commands to compile and link the kernel to the platform design of the U50. These Vitis makefiles on GitHub also typically allow you to run both software and hardware emulation. The software emulation runs quick and validates the functionality of the design, while the hardware emulation relies on hardware description files. For the C++ kernels, it would use the high-level synthesis output RTL files and emulate based on them. Now switching to the application host file. In this version of the project, I am using the Xilinx runtime, also known by its acronym XRT, and its native APIs. It's an alternative to using the OpenCL APIs. We can see in this host file the C++ APIs with XRT : in their names to create the kernel object, allocate the buffers, load and run the Traveler Salesman kernel, and once loaded, execute and read back the information, which in our particular case is simply one result, the shortest route computed for all the cities. Inside the host code, in addition to computing the city distances based on city coordinates, we also compare to golden results, and that's the additional code that you see in this file. The host file makes its calculation using floating point for the distances and retransposes them to 16-bit integers, which are then rescaled to take advantage of their full dynamic range and keep as much precision as possible. Note that if we were to use 32-bit integers or even floating point variables, the kernel would need double the amount of on-chip RAM to store the data, and the route calculation might take more clock cycles and may run at lower kernel clock frequency. At the end of the code, you see the final comparison between the expected result and what's collected from running the kernel. For the kernel code itself, it's the same coding style and structure as we've seen before with the TSP top function that covers the compute subfunction and then the getDistance subfunction. As explained in the slide, the generation of permutation is based on transcoding the long hint of the main loop into a factorial base representation and then mapping that factorial base code into an array that holds all the permutation with 0, 1, 2 up to n-1, each number being present only once. You also see the interface directive with the m_axis setting for the distances, which are stored in a global memory array, while we read the shortest route as a simple scalar. The bind storage directive helps a great deal here, since it gives us a memory configuration that's a perfect fit for what we need. A single write source and several readers. You can see the loop that write into the memory below. Note that we could have used the array partition directive, but this RAM configuration is a better fit for this project. Overall, we basically have three main directives in this design, with interface, bind_storage, and pipeline. They are enough, and the compiler derives other optimization based on the pipeline directive with the automatic unrolling of loops and the parallel scheduling of the replicated compute function calls. At the end of this code, we see the shortest distance computation, which is chosen through the std::min function based on the 4 parallel invocation of compute, each taking care of a fourth of the loop indices, as you see in the loop labeled loop_compute. When you set up the kernel, you can also do so directly in the Vitis IDE, but you can also use the Vitis HLS separately if you wish. Here I'm showing the flow in which you would use the Vitis HLS tool directly. It has its own UI and allows you to create projects. This one is already pre-configured and has the kernel source as well as a test bench, which is the main, and will send the distances to the kernel, as we have seen with the host file earlier. The difference here is that this test bench file does not make any API calls. It only sends and receives data to and from the kernel. The test bench can be used to simply verify the functionality at the C code level, or send test vectors to an already synthesized kernel, in which case an underlying RTL simulator directly called from the Vitis HLS tool is involved. Let me start running the C synthesis for this kernel. It only involves the kernel and takes longer than a simple C compilation, since it will need to implement a microarchitecture based on the user directives that are supplied. It will schedule the necessary operations and associate them with a library of operators and memories in the binding phase. And based on this, it will generate the RTL files that represent the behavior in a hardware design language with a choice between Verilog or VHDL. After compilation, which typically takes a few minutes, the tool displays a report that comes up automatically. That report holds essential information to understand how effective the C code of the accelerated function really is. It gives us general information about the compilation and reports a timing estimate. Lower in the report, we see information about the hardware interfaces and adapters that were added during synthesis, and the association between the C code name for ports and the names in the hardware representation. Then back to the performance and resource estimate section, we access important information that tells us about the throughput and performance metrics for functions and loops, as well as resource estimates. We can see the latency and the initiation interval. If a loop or a function could not meet the II or timing requirement, it would be flagged here. You can click on the expand button with the plus sign over here and see the details for these design elements. What's really important for us here to see is that we have an internal value of 1 for all our loops, which means that we are running the code and processing these loops at each clock cycle in the hardware. In particular, we can read the latency for the critical loop_compute loop. The number of CDs are 13, and the number of iterations for that loop is factorial of 12, the number of CDs minus 1, which is fixed as a starting point. Then, because we are replicating the memories and lookups 4 times in this version of the code, we find exactly the factorial of 12 divided by 4, which amounts to 119,750,400 clock cycles. It clearly dominates the full latency of this design, and if you look at the total on the top of the TSP function, it's also about 119 million clock cycles. Since this version of the design has a 3 nanosecond period, the 119 million clock cycles amount to roughly 4/10 of a second for the kernel execution. The report includes an interface section, and we can see information about our interface for the TSP kernel. It also gives you information about the MAXI adapter, as well as hints and messages as to how well the bursts will be implemented. The bursts are automated by the tool, but they do depend on the coding style. In our case, it's straightforward. We're reading in the data without condition in a clean loop, and there's no issue reading this information while also getting the tool to allow for burst during the data transfers. I would also like to point out another tool within HLS. It's the function graph viewer. It helps understand how the resource and latency are distributed and shows the topology of the design. We see all the different functions and loops in the design, and there is also a heat map functionality to help detect and pinpoint the areas of the design in which you have more latency or maybe worst AI bottlenecks or the biggest consumption of RAM or DSP blocks. This makes it a useful tool to understand the design, and here we are highlighting latency, and you can see that as expected, the loop that we label loop_compute is the one that requires the most latency in the whole design. There is also the Vitis HLS schedule viewer that we discussed earlier. It allows you to understand how the different operations will be sequenced in the hardware. You can see the schedules for all your functions and loops separately. This is another useful tool to debug and better assess the impact of your coding style, or to confirm the microcode architecture is implemented as expected. Once the design is finished, synthesized, and verified, it's time to export. And there are different ways to do it depending on the flow. For the Vitis flow, you export a kernel as a .xo archive. That includes all the files for Vitis to implement the kernel and connect to the platform. So this is it for this quick description of a makefile flow for Vitis and the TSP algorithm acceleration, including using Vitis HLS and some of its analysis tool to design an effective C++ kernel. Okay, so back to the slides. I took the tabulated data that I saw earlier and added the speedup that we can obtain from the FPGA. As you can see from these bars, it's an outstanding acceleration compared to the CPU, and still a sizable acceleration compared to the GPU. Note that this acceleration could be higher. The proposed example only uses 2% of the LUTs and 3% of the DSP blocks in a Xilinx Vertex UltraScale Plus device, the VU9P, for which the dynamic power estimated by the tool is 2.1 watt. Okay, this is now time to wrap up. So we just discussed the Vitis flow and how C++ kernels can optimize untimed portable C++ code to accelerate algorithm via three main pillars of acceleration with the pipeline, SIMD, and DATAFLOW directives. We then illustrated some of the concepts with the traveler salesman problem example, and in which we found a very effective mechanism to generate permutations while implementing a multi-port rhyme structure on chip to read the distances and calculate the cost at blazing speeds and provide orders of magnitude acceleration compared to CPUs, while also running faster than GPUs. For more information about the flow, please point to xilinx.com/Vitis and stay tuned during the Q&A session for more information. Thank you very much and see you next time. Bye-bye.